Basically what this is just a different way of writing the derivative of a function and then using it. Yeah. It's basically a differential. We know when we did derivatives, one way we wrote that was dy dx, right? Remember that? And the derivative of a function is basically the slope, right? So this is like slope. Or, change in y over the change in x. That's basically what that represents. A differential function is just basically the same thing, just written differently. So like, if we have a function y equals f of x, if I do the derivative of that function, well now dy dx equals f prime of x. The way differential equations are written is we just imagine multiplying both sides by dx. So dy would equal f prime of x dx. It basically gives you the change in y as a function of the change in x. So this would be like the dependent variable. The change in y would depend on the change in x, and the function, of course. And I think this will make a lot more sense once we start doing some real examples. We'll start with some not so real examples. But just to give you an idea of how to write these, let's say we had, something like y equals x to the third plus 2x squared. You know how to find the derivative of that. So the derivative of this, derivative of y, remember we always would just do dy dx equals 3x squared plus 4x. And that's the derivative, right? Well, to do a differential, there's two ways of doing it. You could either do it this way and then multiply both sides by dx. So now we have dy equals 3x squared plus 4x dx. That just gives us the change in y as a function of the change in x. Or, which I think you'll find easier on these, if we have that same function, we basically just go through and take the derivative of each piece. So like y would be dy, x to the third would be 3x squared dx plus, and then 2x squared would be 4x dx. And now just factor. These both have dx in common. So dy equals 3x squared plus 4x dx. End up with the same thing, just a different way of thinking about it. Like I said, it's just doing the derivative. And once we get to the real world examples, you will understand this a lot more better. It's a good word right there. Alright, so these are not real world examples. This is just an idea of what we're going to do. Am I on the screen? Yeah, looks good. Alright. So let's say we have a function y equals the sine of 3x. And let's say at x equals pi, the change in x will be negative 0.02. What we want to do here is find dy and evaluate it for these givens. Maybe I should have done the real world ones first. So I'll do a real world one after this. Well, so doing the derivative of this, I'll just go across, and I'm going to do it the other way. So dy will equal, derivative of sine of 3 of x will be cos of 3x, and then chain rule, right? Derivative of 3x is 3, so it's 3 cos of 3x dx. And now this is just saying when x is pi, and then we want x to change by 0.02, so we just plug these in. So dy will equal 3 times the cosine of 3 pi times negative 0.02. And so if we calculate that, you just have 3 cos of 3 pi negative 0.02, 0.06. So you may be wondering, what is going on? What does this all mean? Like I said, let's do a different example. Wasn't going to do this next, but I'm realizing that it's not making sense if I don't do this next. So let's do this one. This is just out of the book. It's example 7. It says the radius of a circle increases from 10 meters to 10.1 meters. We want to use this. Basically, we're going to find the increase in the area. Using the derivative, we're not going to do. I mean, this is just doing these differentials is just an approximation. So, let's see here. So we know area of a circle, right? I hope. Am I on the screen? Yeah. Area of a circle, pi r squared. Doing the derivative of that, and like I'm going to do the new way. I'm going to do this way. I'm not going to do the old way, so bear with me. If I just go across, doing the derivative, it would be dA equals. The derivative of that would be, I bring the pi as a constant, so it would just be 2 pi r, right? Drop the 2 down, subtract 1 from the power. So it would be 2 pi r dr. I mean, if you did it the old-fashioned way, you'd have dA over dr equals 2 pi r, multiply both sides by dr. Same thing. So this basically means the change in area equals 2 pi times the radius times the change in the radius from whatever the original radius was. So we can use that to calculate the change in area. So if we do that, we're finding the increase in area. So remember, dA basically just means change in area. So dA will equal 2 pi. The radius, the original radius was 10. And it moved up to 10.1. So the change in the radius is just 0.1. And if I multiply that out, 10 times 0.1 is 1. So I just get 2 pi. So the change in the area as the radius increased from 10 to 10.1 was 2 pi, I guess it would be meter squared. Does that make a little more sense as to what these are? So like back here, the change in y value of this function depends on, if x was originally pi and then it went down to, 0.02, then the change in the y value of the function would be 0.06. So as x moved to the left 0.02, the value of this function actually went up 0.06. Here, as the radius of the circle increased by 0.1, the area of the circle increased by 2 pi. And that's, like I said, this is just an approximation, kind of like our linear approximations we were doing. Because if we do the actual area equals pi r squared. So pi times 10 squared versus pi times 10.1 squared. Let's see how far were we off. 100 pi. This would be 3, 4, 5, 9. And the other one would be 320.473. Oops. So our actual change, if I subtract those, oops, the change was 6.3146. We got 2 pi, and 2 pi is 6.283, so we're pretty close. Our calculated change in area doing it this way was 6.28. The real change in area was 6.31. Pretty close. And this is basically how your homework is today. Just do a couple more here. Let's go back. Do one of the non-real ones again. So let's say we have a function, or maybe it's not a function, but just equation x plus y equals xy. And let's let x equals 2 and dx equals 0.05. We're going to find dy. So you remember implicit differentiation where we went across and like derivative of x is 1 plus derivative of y is 1, but dy dx, remember you had to add the dy dx in there every time. We could do it that way. I mean, I wish I was there to ask you what you all prefer, but we're just going to do it the new way. So going across, taking the derivative of that, derivative of x, I'm just going to go dx plus derivative of y, dy equals, now I have to do product rule. So I'll do the first one times the derivative of the second plus the second one times the derivative of the first. And I want to solve for dy here. So I'll get everything with dy to one side. So I'll subtract dx and subtract, I'm going to do it all in one step here. Should have wrote that over further. Subtract x dy over to this side. So these are going to go away. So I'll have dy minus x dy equals, let's see, x dy, I subtracted that over. So y dx, it doesn't matter what order you write these in, minus dx. Pausing for a minute, let that sink in. I feel like I've been going really fast. So wait a second. Okay, so I want to solve for dy, so I'll factor out the dy. And I'll have 1 minus x. And I'm also going to factor out dx here. You'll see why. So I'll have dx times y minus 1. But now, thing is, well, I guess we could finish here. Divide by 1 minus x. Divide by 1 minus x. So the change in y is equal to the change in x times y minus 1 over 1 minus x. Okay, well, that's right, it's correct, but there's a y in our change in y. So we need to get rid of that. I don't know if, again, if I was there, I would ask you if you had any ideas of how we would get rid of that. But I'm not, so we're going to take the original equation and get rid of that y. So I know x plus y equals xy, so now let's solve for y in terms of x. This might not work. We'll see what happens. If it doesn't, I have another method. I haven't actually tried this yet, so this is a good exploration. So let's solve for y here. Well, how am I going to do that? I guess I'll subtract y from both sides. So I have x equals xy minus y. And I'm going to flip sides just because of personal preference. Xy minus y equals x. Factor out a y there, so y will equal x minus 1, or y times x minus 1, sorry, equals x divided by x minus 1. Hey, it worked. So y equals x divided by x minus 1. That's nice. Now we can plug that back in. So my real dy will equal dx times x over x minus 1 minus 1 over 1 minus x. So now I just gotta plug stuff in. Just checking the screen here. Plug stuff in. X is 2, dx is 0.5. Alright, so dx is 0.05 times 2 over 2 minus 1 minus 1 over 1 minus 2. Easy deal now, just clean this up here. 2 minus 1 is 1, 2 over 1 is 2, 2 minus 1 is 1, so on top I have 0.05. And on the bottom, 1 minus 2 is negative 1. So my answer then, my change in y, is negative 0.05. Wasn't that fun? Hopefully you're getting the idea, seeing that this is just pretty easy. Do one more example here. I think. Yeah, I've already done that one. So here's another one. Got the radius of a sphere. Keep in mind it's a sphere, not a circle. Was measured to be 21 centimeters with a possible error of plus or minus 0.05 centimeters. And I assume you've talked about error in measurement in science, meaning they measured it, but they could be off by that much. So the question is, what is the maximum error in volume using this measurement? I feel like I'm actually there with you guys right now. I'm really hungry. So what's the max error in volume using this measurement? Alright. Well, the volume of a sphere, wouldn't expect you to come up with this, is, let's see, what is it? Got it written down over here. Volume of a sphere is 4/3 pi r cubed. That'll be given to you in these types of problems. So here we go. Max error in volume. Basically, what we're going to do is, the whole idea here, we could calculate the volume using this measurement, but it's like these. What would the change in volume be? So that'd be the error in the volume. If we change the radius by 0.05 centimeters. And every time I say change, you should be thinking in your head, if I say change in volume, you should be thinking, oh, dV. If I say change in radius, you should be thinking dr. So that should lead you to go, oh, if I differentiate this and turn it into a differential equation, I can use my differential equation to calculate the error in the volume. So let's take the derivative of that. So dV, change in volume, will equal. If I do the derivative of this side, I drop that 3, it would be 4/3 pi and then 3r squared. Well, 4/3 times 3. Wish I was there to call on Nicole. What's 4/3 times 3? Oh yeah, it's 4. Oh yeah, good job. So it's 4 pi r squared. And then dr. Alright, so now we've got our equation, we just need to plug stuff in. So our change in volume, when the radius is 21, so I'm going to plug that in, so I'll have 4 pi times 21 squared. So when the radius is 21, but now the change in radius, if I change that by 0.05, and the plus or minus doesn't matter, I mean, you're just going to get a different change. So I'll just plug in 0.05, that would be my maximum error. If I change the radius by 0.05, what will the change in the volume be? Just calculator it. 21 squared times 4 pi times 0.05. So I get my change in volume to be 277.09. What is this? Centimeters cubed. Right. And you, well, that's the answer, and that's probably good enough for this class and for the AP test. Where I see my video is only 22 minutes long, so we can go a little further. Talk about relative error and percentage error. I don't know how much we actually need to go into that. My guess is it's very, that we don't really. What relative error means is basically, you got this as your change in volume, and you may be thinking, 277 centimeters cubed, is that big? Is that small? Is that a huge difference in the volume from the original, or is that a small difference? Maybe we don't want to talk about this. It's kind of like a who cares. It's kind of like a statistics thing. Basically, you would just have to, figure out your total volume and then divide and see what percentage of this error is of your total volume. That would be percent error or relative error. I don't think we want to go into that. It's really boring, and I don't think it'll be on your AP test. When we start looking at AP questions, if we decide it is important, it won't be that hard to fill in later. As long as you get this main idea of how to do these differential equations, that's good. So let's see, maybe we should do one more. Or maybe not. I don't know what to do. Yeah, one more. And you can pause this one to try it on your own to see if you get the idea. I wasn't planning on doing this, so I'll just pick one out of the book here. Let's go with, right here. So if we inflate a bicycle tire, the radius changes from inches to 13 inches, right? Because if it's flat, it'll be smaller. You put air in it, it's going to get bigger. We're going to now find the change. In the perimeter of the tire. Now this one, before you pause it, this one, you could do it two ways. You could find the perimeter of a 12-inch radius tire, or you could find the perimeter, and then you could find the perimeter of a 13-inch radius tire, subtract them, and find the change. And that'll work, but let's just use this new way of doing things for this one. Because you'll see why later. Because there are problems that you can't just do that. So, if you want, pause it now. And then I'll do it here in a second. Oh, you probably need to know. Hopefully you haven't paused it yet. The perimeter of the tire. Think about perimeter of a circle. It's circumference, right? It's 2 pi r. Hopefully you remembered that. Now you can pause it if you didn't remember that. Or maybe you're hitting play after struggling and hopefully you thought of that. I don't know what's going on. It's probably pretty funny in there right now. Okay, so now I'm going to do it. So we want to find the change in the perimeter. That'll be dp. We'll have to change in radius. So take the derivative of that. So dp will equal derivative of 2 pi r. Well, isn't that just 2 pi? Because the r will go away. So that's just 2 pi dr. So the change in perimeter will equal 2 pi times the change in the radius. Well, change in the radius is just 1. So 2 pi times 1 is just 2 pi. So the change in the perimeter is 2 pi inches. That's about as easy as it could be. So that's all. Here you go. Where did I write that down? Do 5.5, number 6. That's a review from yesterday. So it's 14. The new ones will be 15, 16, 31, 32. These two would be like the ones that we're doing at first. With like y equals sine 3x, given x and change in x, find the change in y. And these two are more like these story problem types. Checking to make sure I'm on the screen. And then the directions on these two are kind of confusing. So look at them now. Go to 5.5, look at 31 and 32. And if you look, it says, in the directions, it says, in exercise 31 and 36, write a differential formula that estimates the blah, 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 blah. Who cares? But then the important part says, estimate the change when the independent variable changes from 10 centimeters to 10.05 centimeters. So from 10 to 10.05. So like on 31, it says the change in the volume of a sphere when the radius changes from a to a plus dr. So what they mean there by that a to a plus dr is they mean from 10 to 10.05. So like this one will be find the given, they give you the formula for volume and they want you to find the change in volume when the radius changes from 10 to 10.05. So again, like 31, find the change in volume when the radius changes from 10 to 10.05. It's kind of worded weird, but I thought I'd point that out. Same thing on 32. It's just surface area. Gives you the formula for surface area. Find the change in surface area when the radius changes from 10 to 10.05. Those should be pretty simple, but I wanted to give you simple ones just to see how you're handling this. Hopefully it'll be a simple thing, and tomorrow we can do some harder ones and then maybe even move on to related rates, because those are a little harder.